Let's get into the design of CMOS logic gates. We will be mainly using two gates. One is this gate. This is what is called PMOS, and the behavior is like this one. So if you give it, this is the gate, this is source, drain. If you gave it a 0, the gate 0, so the source and drain will be shorted. If you gave it a 0, the source and drain will get shorted. If you gave it 1, it will be open. The source and drain will be open. This is the source, this is the drain. It will be an open circuit when the gate is 1. So this is PMOS. Then we have NMOS. NMOS is this one. It doesn't have a bubble at the gate. This is gate, source, drain, and it is reverse. If gate is 0, it is an open switch. And if gate is 1, it is like a closed switch. Okay, so this is like the things that you have to keep in mind. Now what we want to do, we want to design a 4-input CMOS gate. We want to design a 4-input CMOS gate. Okay. Let me go to the previous slide. Okay, this one. So now we have to remember that a CMOS gate has two parts. One is called the pull down, okay, and the other is called pull up. The pull down is composed of NMOS and the pull up is composed of PMOS. So any CMOS gate is a combination of both NMOS and PMOS. Okay, now the second thing that you have to understand is that the CMOS technology is complementing. What this means? This means that naturally you can build NOR gates, NAND gates, and NOT gate more easily than other gates. Okay, so And let's start with the design of 4 input NOR gate. So we will have a pull down network. Let's go back. We'll have a pull down network which will consist of NMOS. So we have 4 NMOS. And all the NMOS are connected to, they are connected to ground. So this is ground, 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 ground. And they are connected to, for example, A, this is connected to B, it's connected to C, this is connected to D. And all these are then connected to our output. So for example, this may be Y, which is a function of A, B, C, D. So this is the pull down network. This is the pull down network. So this is in parallel. So in parallel, it's like an OR operation. It's like OR type operation. So if this is 1, if A is 1 or B is 1 or C is 1 or D is 1, so the output will be 1. It means any of these is 1, the output is 1. So this is called the pull down network. And then every CMOS gate should have a pull down and a pull up network. So the pull up network should be consisting of PMOS. Okay, 1, 2, 3, 4. So it is shorted with this point, and this is A, B, C, and D. And this is our VCC or VDD. This is our supply. So you see, this network is called pull up network, and the resultant is our NOR gate. So how you can confirm that this is a NOR gate? You can apply the inputs, okay, all the inputs A, B, C, and you can check the result. For example, let's say that if A is 0, B is 0, C is 0, and D is 0, what is the value of Y? We can check. So if A is 0, B is 0, C is 0, D is 0, this is 0, this is 0, this is 0, and this is 0, okay, all the pull down network will be open. All the pull down network will be open. So the A, B, C, D switches will be open, and all the pull up network will be closed. So this will mean that the VDD is connected to output, which will mean that our output is 1. So in a similar manner, we can find what is the output if A is 0, B is 0, C is 0 and D is 1. Okay, for this, what is our output? So now in this case, this is 1, D is 1 and D is 1. What this means, that this is closed, A PMOS is closed, B PMOS is closed, C PMOS is closed, but D is, this one is open. So this one is open. So it means that the VCC is not connected to Y. And if we come here to the pull down network, so this is open, this is open, this is open, but this one is closed. This one is closed. And that means that the ground is connected to our output Y. So that will mean that our output is 0. So in a similar manner, we can try all the input combinations. How many input combinations are there? There are 2 raised to the power 4 input combinations, which are 16. And in this way, we can generate the whole truth table for the NOR gate. And you will see that the results are according to the NOR gate. So things to remember. We use pull down network, which consists of NMOS gates, and we use pull up networks, which consist of PMOS gates. It is called pull up because it is connected to VDD, and it is called pull down because it is connected to ground. So down for ground, up for VDD. Okay, if you want to design OR type function, OR type operation, so the connection should be in parallel. Okay, and if you want AND type of operation, the connection should be in series. So why this is in parallel? You see the pull down is in parallel. It's because we want this function A, B, C, D, which is A or B or C or D. The plus is for OR. Okay. And if we come to the pull up network, it is basically Y bar. And Y bar is what? Y bar is A plus B plus C plus D bar. Okay, which means if I apply De Morgan's law, it is A bar, the OR will be converted to AND, B bar, C bar and D bar. So you see that this is the circuit. So what this means is every OR gate, every CMOS gate will have both F connected in pull down network and it will have F bar connected in pull up network. So that is the main design principle: pull up, pull down. Okay, and you have to remember, if you are designing OR type gates, use parallel. If you are designing AND type gates, for example NAND, then you use series connection. Okay, let's move on to the next slide. The next slide has the 4 input CMOS NOR gate. Okay, so this is again the whole story, that we have inputs coming in and it goes to both to the pull up network PUN and to the pull down network PDN. And now you know that the pull up network is composed of PMOS and the pull down network is composed of NMOS, and the output is between these two networks. So this is connected to our VDD or VCC, which is a supply, and this is connected to our ground. This is the structure of our CMOS gates. And what kind of output can we expect? So in the table, if we have the pull down is off and the pull up is off, so if the both of these are off, what this means that the voltage at the output is not known, so it is called floating. So if we are both the networks are off, then there is no voltage, and this is called floating or high impedance. Now the second scenario is this one at the corner. Let's say if this is on and this is on, both are on, then one is driving a high voltage on the output and the other is driving a low voltage on the output. So here we have a race condition. This is called race condition. So we use X for this, Z for this one, and X for this one, and the other are normal cases. So let's say the pull down is off, so we are not pulling down the circuit to ground, and the pull up is on, so means that the output is logic 1. In the other case, when the pull down is on and the pull up is off, this means the output is logic 0. So this is just the summary of what are the possible outputs that you can expect from a CMOS gate. There are 4 possible outcomes. Let's where is it? Let me come back to this one. Okay, so series and parallel. So we have already discussed for a series, if we have 2 transistors, for example this one, if you want them to conduct, both of them should be on. So this should be on and this should be on. If any of them is off, the output is off. So this is for NMOS. For PMOS, both should be 0, then both the gates should be 0, then it will be on, otherwise it is off. For NMOS in parallel, if any one is 1, any one of the gates is 1, the output is 1. So this is basically you can say OR type of operation. Both these are AND type Okay, this is OR type. So this is also, this is parallel, so OR type. Okay, so as I told you that in CMOS you can build inverting gates. So it's easy to build inverting gates. For example, you can easily build NOR gate, you can easily build NAND gate. Okay, so for example, if I want you to build OR gate, how I will build OR gate? I will first build a NOR gate. Okay, so this is my NOR gate which we discussed in our previous slide, and then I will build a NOT gate. Okay, and I will connect the NOT gate in front of it, so this will become OR gate. Okay, so this is called conduction complement. So complementary CMOS gates always produce zeros or ones. Example is, for example, this is a NAND gate. You see why this is a NAND gate? Because if I look to the pull down network, the pull down network is of type N type. They are series. Okay, so it means that our F is basically A and B bar. Okay, so our F bar should be A and B bar whole bar, which means our F bar is A bar plus B bar if I apply this complement inside whole bar. And you see that this is exactly what our pull up network is. It is OR type, parallel, and because of this bar we have PMOS. So because of this bar we use PMOS. So this is how we construct a NAND gate. So what is the difference between the NOR, which we designed in the previous slide, and this one? In the NOR, the pull down network was OR type or parallel, and the F bar was N type or series. In the NAND gate it is opposite. The pull down network is N type or series, and the pull up network is OR type or parallel. So this is the story. Let's come to another gate, which is the compound gate. So basically the equation is this one: y is equal to A and B plus C and D, and there is a whole bar on it. Okay, so first we develop A and B. So this is A and B, this is series, this is C and D. Okay, this one, and you combine it in parallel, this is AB plus CD. Okay, and now this one, So this is our pull down network, and this is our pull up network. So you see, the pull up network should be this one, AB plus CD. So our original Y was that one, it has 1 bar, and our Y bar has 2 bars, so it should be A, B bar. Okay, so this bar is come here, dot CD bar. So we have only applied the internal bar, and now we will apply this bar, so it will become A bar, B into C bar, D bar, and we have this whole bar. So you see, this one is A bar plus B bar, this one is C bar plus D bar, and this one is A bar plus B bar ended with C bar plus D bar. So they are connected in series. So this is our pull up network. Now if you combine this, you see this is our pull up network, and this is our pull down network. So now the complete integration of pull up and pull down results in our desired gate, which is YAB plus CD bar. So this is our whole compound gates. Okay, this is the design principle for building up CMOS compound gates. Always the procedure is same: design the pull down, design the pull up, connect the pull up to VCC, connect the pull down to ground, and you get your function implemented. Okay. So here is another one. So we have to implement this function, which is Y is equal to A plus B plus C, and then we have an and then bar. So first we will implement the pull down network, and the pull down network is what? It has A, B and C connected in OR type or parallel, and then after this we have this connected with D, which is series connection, and our output Y is here. Okay, so this is our pull down network. What will be our pull up network? It will be A plus B plus C double bar. So this is our Y bar, which will mean that A plus B plus C bar plus D bar, and we have this whole bar here, and we will have A bar dot B bar dot C bar plus D bar and the external bar. So what this means is that the pull up network has this equation, which means that we have a PMOS A, a PMOS B and a PMOS C connected in series in AND type fashion, and we have with this we have a PMOS D connected, this is connected to VCC or VDD, connected here, okay, and then it's connected here. So this is 1 point. So this is our pull up network, this is our pull down network. So this is the design of this compound gate. Okay, let's stop here.